Yeah, so we're very happy today that we have David Nichols. David is a theoretical physicist who is interested in black holes, neutron stars, gravitational waves. He received his PhD in 2012 from Caltech, and now he's on the faculty at the University of Virginia. So today he's going to tell us about gravitational wave memory effects in black hole binary mergers. David, take it away.
Okay. Well, yeah, thank you very much for that nice introduction and for the opportunity to give this virtual black hole colloquium. I hope to actually visit the Black Hole Initiative at some point. So let me just give you a brief outline of what I'm going to cover today. So what I'll do is I'll just give you a very brief review and summary of sort of the status of gravitational wave detections before moving into my focus of the gravitational wave memory effect, where I'll talk about sort of both the prospects and then some of the theoretical implications of discovering the gravitational wave memory. And I'll conclude by describing some new kinds of gravitational wave memory effects and what their detection prospects are. So let me then begin by just describing that, as you're probably aware, in general relativity, there are two polarizations of gravitational waves, the plus and cross modes. And they produce strains, which are something that laser interferometers can measure. So in this nice animation by LIGO, what's going to happen is a gravitational wave will come down from the top. It'll cause stretching and squeezing of the two arms, and this leads to some light leaking out of the interferometer, which can be calibrated into a strain. And this has been done on an extremely large scale in the two 4-kilometer LIGO interferometers in the USA and the one Virgo interferometer in Europe, which is 3 kilometers. And their sensitivity is shown in this bottom panel here, where the strain noise as a function of frequency is given for the 3 interferometers. And what this means in sort of physical terms is that over these kilometer scale interferometers, one is capable of measuring distances which are some extremely small fraction of an atomic nucleus, several tens of thousands. So it's a remarkable experimental achievement. The network is going to grow shortly. The KAGRA detector has been constructed and is being commissioned in an underground mine in Kamioka in Japan, and will soon join this experimental effort. Despite the fact that gravitational wave detectors are extremely sensitive, you still need to know precisely what the two polarizations are to be able to extract them from the noisy data. And for binary black holes, the waveform is usually broken into 3 stages: the in-spiral, merger, and ring down. The in-spiral is this slow adiabatic shrinking of the orbital separation, during which the amplitude of the waves increases and the frequency increases. The merger is the transition between 2 individual black holes and a single black hole, during which the waveforms hit their peak. And the ring down stage is the final stage, during which the highly distorted black hole settles to just a single isolated Kerr black hole. And in this evolution of frequency and amplitude, there's precise information about the masses and spins of the black holes that can be extracted through various data analysis procedures. And the result of this experimental and data analysis procedures is highlighted in this figure here from the LIGO and Virgo collaborations. What it shows is blue dots are the masses of all the black holes it's detected. As orange dots, it shows the neutron stars it's detected. And as these 3 gray dots, these are objects where the gravitational wave data alone can't tell you whether it's a black hole or a neutron star. So I've just highlighted sort of what the pace of the discovery has been, and as you can see, it's been rapidly increasing from the first observing run when there were 3 binary black holes detected over 3 months, to the third observing run where over a 6-month period there have been 36 black holes, 1 binary neutron star, then 1 interesting possible black hole neutron star candidate, and another most likely binary black hole, which contains one of these objects, which is either the lightest black hole discovered to date or the heaviest neutron star. Okay, so what this image, I believe, nicely shows is that we're entering sort of the stage where there's a large number of black hole detections, and we can start understanding some of the more precise physics of binary black hole mergers. And to motivate why one would want to do this, I'll show the following figure here, where I have gravitational wave luminosity shown on the vertical axis, which I've plotted in units of the so-called Planck luminosity, the unique luminosity you can construct from Planck's constant, the speed of light.
Sorry, could I just ask, is that, you said 3 in 3 months and then 36 in 6 months. Is that less than they originally, less of an improvement than they originally thought they would get? And is this Kamioka gonna expected to push that up quite a bit?
So yeah, I'm trying to think. I guess the median value of the rate has decreased slightly from the initial estimates based on the first 3 detections, but it's consistent within the error bars of what they found in terms of the rates. And the main advantage of adding the KAGRA detector in Japan is that it'll improve localization, and also these detectors aren't operational all the time. There's some duty factor. So having 4 detectors means you're more likely to have 2 operational at any given time. So that will also improve the number of detections.
So slightly more events, but mostly more information about each event.
That's right, yeah. Okay, so yeah, let me go back to motivating why binary black holes are interesting and are sort of probing a new parameter space. So this Planck luminosity, what I'm using it to represent is how dynamical the space-time is. So for large values of this Planck luminosity, this means the space-time is evolving very rapidly due to gravitational waves. And on the horizontal axis, I'm showing the separation of a binary in terms of its gravitational radii, or you can think of this as a dimensionless Newtonian potential. And when this quantity is of order 1, it means the binary is so compact that a black hole would form. So I'll just show a few characteristic systems, one in the solar system, which is Mercury and the Sun, which if you naively plug in the quadrupole formula, radiates about 1 watt of gravitational waves. So you'd never really hope to measure any gravitational wave phenomena from this. And of course, it wasn't until the discovery of binary pulsars that there was actually compelling evidence for the existence of gravitational waves. And the reason being is these are both much more nonlinear, or more strongly self-gravitating, and they're also radiating a gravitational wave luminosity comparable to the solar luminosity. But these binary black holes are in a completely different parameter space here. They're up in this top corner, where for a brief moment, they're radiating at around 1,000th of this Planck luminosity, this fundamental limit of luminosity. So just as you would never attempt to measure gravitational waves using Mercury and the Sun, you're going to be able to probe new kinds of gravitational phenomena with binary black holes that just aren't really accessible to widely separated systems like binary pulsars. And the focus of this talk will be on the gravitational wave memory effect, which is one such phenomenon. So to give a schematic picture of what this is, I've shown 2 gravitational waves, which are similar, except for the fact that the one shown in blue goes to some non-zero value at late times, which I've denoted by delta H. And if you think about what this means for an idealized interferometer, like the schematic movie I showed at the beginning, for the red gravitational waves, the ones without memory, if the interferometer starts in some equal arm length configuration, it'll end in the same configuration at late times. However, in the case where there's memory, if the interferometer starts with equal arm lengths, it'll end in a distorted state. So in an idealized LIGO, there really would be light leaking out of the dark port after the gravitational waves have passed. And this memory effect is a prediction of general relativity, which is expected for most transient gravitational wave sources. So let me describe the kinds of sources that produce gravitational wave memory. I have this schematic formula here. I have a cryptically named quantity, which I'm calling changes in conserved quantities. And I'll define this more precisely later, but for now you can think of this as any system that results in some change in its quadrupole moment at late times. So one example, and where it was first discovered, was in the scattering of compact objects like black holes and neutron stars. This can produce a gravitational wave memory effect. But there's two other kinds of sources, both of which involve cumulative effects involving integrals of the energy flux per solid angle in massless particles and in gravitational waves. So for the massless particles, it was first discovered for nearly massless particles, namely neutrinos that are emitted during the core collapse of supernova. And it was understood that in this collapse process, the asymmetry in the radiation of neutrinos can source gravitational waves. And something very similar happens for the flux of gravitational waves themselves. This was discovered by Christodoulou, and it's a nonlinear gravitational wave effect. And it's essentially identical, though, to this other term in the sense that it's the energy per solid angle radiated in gravitational waves that produces this non-zero change in the strain at late times. So one can understand this in terms of a Newtonian picture relatively easily. So imagine you have some binary, which is widely separated, and it begins inspiraling, so the separation A decreases with time. If you compute the memory from this, it turns out to appear just in the plus polarization, and it's proportional just to the change in the binding energy, which is reasonable because as the two black holes move closer together, then some binding energy is radiated in gravitational waves to make this happen. And this radiation of energy produces these secondary waves, which is the memory. And this was something that was computed soon after the discovery of the memory effect. However, it turns out that the part of the memory associated with this slow in-spiral is actually very weak. So what I'm showing here is the result of a full numerical simulation of emerging black holes done by Keith Minton and collaborators. And the part where the Newtonian approximation works reasonably well is between these dashed green lines. And the full result of their simulation is shown in black. And most of the memory actually accumulates in a short time right around the merger of the black holes. And just as an interesting note, there's this quantity J here shown in red. And this this term basically shows the result using the approximate formula I showed on the previous slide. So it agrees very well with what you'd expect, that it's just simply, it's mostly produced by the radiation, the energy radiated in gravitational waves. Okay, so I'm interested in attempting to detect this gravitational wave memory effect, but of course the memory effect, the waveform doesn't appear in isolation. It always appears with these accompanying in-spiral merger ring-down waves, which I showed previously. So it turns out the amplitude of this effect is relatively small. I'm just comparing the waveform without the memory versus the full exact waveform that you would expect, which would have memory. And as you can see, there's only some slight difference at late times where there's a small offset. So the question from the detection standpoint is, which waveform would be preferred by the data? The one where there's a small offset or the one where there's not? And to assess this, I'll just look at what is the additional signal to noise contributed by this non-zero mean part of the waveform, the one that goes to a constant value. And the signal to noise you can just think of as sort of the significance in sigma of the signal. So what I'm showing here is what you would expect.
Do you have to also worry here about the fact that the pendulum swings back and erases the memory effect?
Yeah, so LIGO won't be able to measure this constant offset at late times, but what it will be able to measure is the fact that this waveform has rapidly ramped up. So there's some time scale associated with this, which is roughly about the length of the merger time. So it's a few say 50 or so m in geometric units. So there's some timescale associated with this, and this is what you actually measure with LIGO. But you don't measure this lasting offset because LIGO isn't truly freely falling.
Right. So how much trouble does that give you? The fact that the pendulum swings back.
I mean,
you have to measure it before the pendulum comes back, right? So how far is that on this picture?
Yes. So essentially, if you think about this in the frequency domain, this offset is a zero frequency effect, but LIGO only measures up to some fixed frequency, about 10 hertz. So what turns out to be the loudest part of your signal, the part that approaches zero frequency, gets cut off, but there's some residual part above 10 hertz that you can measure. And that's what I've that's what I'm computing on the next slide.
10 hertz, I see.
Mm. So yeah, so with this caveat, this is what the signal to noise of this, how the memory accumulates is. It's not the DC offset, but it's what LIGO can measure of this signal. And yeah, if there are experts in the audience, this is for advanced LIGO at its design sensitivity for a single detector, and I'm averaging over sky location and orientations of the binary. So it's not the best case scenario, but best case scenario might be a factor of 2 or 3 better, but it's sort of what you might expect on average. So each of these gold stars represents a detection, so the distance and then the total mass of the system in which it's detected. So as one can see, the signal to noises are all below 1, and to have something where the signal to noise is of order 3, which would be a 3 sigma significant detection, you need something at least an order of magnitude closer. So the rates of this will be relatively low.
So David, just to understand, how do you separate the memory effect? I mean, you said that there is this time-dependent rise that you're looking for, but how do you separate it from just, the gravitational wave signal, that the oscillatory part? So is it separable, and how do you do that?
Yeah, so the theorist's version of the data analysis is you essentially subtract off the maximum likelihood waveform and you're left with some residual signal. So that's sort of the theorist's explanation for what you would do. In practice, what you would actually do is you would do a hypothesis test. You would say, is this bottom signal here preferred by the data, or is the top signal? So you can look at, say, an evidence ratio or a likelihood ratio for the two signals. Okay. And see which the data actually prefers. Is there this additional rise, or does this rise not exist in the data?
But in principle, given your best fit to the rest of the data, you can forecast, if you assume general relativity, you can forecast how big is the memory effect that you should expect, and then see if that's what you're seeing, right? So in other words, GR predicts what the memory effect should be, right?
That's right. Yeah, and I believe I think what I'm computing is what you're saying.
That's what he did on the bottom picture, I think.
No, but does it carry any new information? So in other words, if we know already how much energy was carried by the waves, then we know what the memory effect to expect, and it doesn't give you any more information because we measured already how much energy is radiated. So is there any new information in what you're doing? That's what I'm asking.
So you don't directly measure how much energy is radiated, right? I mean, that's something that I guess you would infer. And then the other thing is that this memory isn't just the total energy that's radiated. It's something like the asymmetry in the sky pattern of the energy that's radiated. So it contains distinct information.
So you have some additional information about geometry as a result of measuring the memory effect. That's what you're saying.
It depends on the inclination angle at which it's observed. So if you observe the binary face on, you actually don't see any memory effect, so along the orbital angular momentum. And if you observe it edge on, then that's when the memory effect is strongest.
Okay.
It's also a very fundamental test of GR.
Right, but what we are
qualitatively different than anything that's been done before.
But why is it qualitatively different?
Well, there's It has to do with very subtle properties of the infrared structure of GR, the symmetry structure and the infrared structure of GR that you know were missed until essentially the work of Bondi, Metzner, and Sachs in the 60s. It's not like gravitational waves. It's not a simple thing.
Right, but
it's a very subtle. It's a very subtle effect.
Are there theories of gravity that have a very different memory effect but the same gravitational wave signal? Or is energy conservation pretty much requires the memory?
It's not just energy conservation.
Yeah, so I'll explain this in about 3 slides. So if you're willing to wait for that long, I hope I'll at least address the question. If I don't, then ask it again. Okay, so, but before I discuss these issues about what the memory means, I just want to say a few more words about detection prospects. So the point of this slide is that it looks unlikely that advanced LIGO will detect it from a single observation. So there are 2 things that one can do then. One can either wait for better detectors. So there is the so-called 3rd generation of gravitational wave detectors. One is planned to be in Europe, called Einstein Telescope. It's 10 kilometers underground. If everything goes well, it'll be operational in the 2030s. And there's Cosmic Explorer, which is a US-led project. It'll be 10 times the size of LIGO above ground. And it'll come in 2 stages, one in the late 2030s, one in the late 2040s. So as you can see from these noise curves, blue is advanced LIGO, green is Einstein Telescope, and pink is Cosmic Explorer. So these detectors are about a factor of 20 to 30 times more sensitive than advanced LIGO. So the noise level is significantly lower, and one can then look at what the equivalent signal to noise is for the memory effect in these 3rd generation detectors. And again, this is the angle average, so not even the most optimistic scenario. So with Cosmic Explorer, there's going to be several detections where there's memories detected at least of, the signal to noise at least of 10, and possibly higher. And then Einstein Telescope isn't quite as optimistic, but there will be significant detections of it. The other thing that one can try to do is look for the presence of the memory effect in a population of binary black holes. And the idea basically is to look at a total signal to noise of this population, which is just a sum and quadrature of the individual signal to noise square root. So then this total signal to noise grows roughly like the square root of the number of events that you have. And this idea was originally proposed by Paul Lasky and collaborators, and they considered a very simple population of detections just like the first event, in which the location and the masses and the distance were the same as the event, but the sky location and the orientation of the binary differed. And they made many realizations of these populations. So one such realization is shown in gray here. And then they averaged over these different realizations to find the total signal to noise. Now, it turns out there's one slightly subtle issue that if you only measure the quadrupole part of the waves, it's very hard to distinguish between a memory effect that, say, stretches the X arm of the detector or the Y arm of the detector. So you can't truly do this coherent stacking procedure, which I've described here. But if you ignore the set of events where you don't measure the higher modes, that's what's shown in red. And if you keep all the events, that's what's shown in blue. So it doesn't actually make a huge difference. And if you have on the order of, say, 30 events where you, like the first 150914 event, you could measure the memory effect in the population, not of any individual events, but with a 3 sigma significance. And if you have 4 to 90 events, then it becomes 5 sigma. The main limitation of this study was the very specific population that they considered, which was just sort of a proof of principle population. So with the master's student Oliver Boersma, we revised this calculation and looked at what happens if you actually have a more realistic binary black hole population, which was the population consistent with the first two observing runs of the LIGO and Virgo detectors. And what you can see, we've plotted this instead of as a function of detections, as a function of detector operation time, assuming that we have 2 LIGO detectors and 1 Virgo detector at the design sensitivity, and they operate with a 50% duty cycle, meaning that in the 5 calendar years of operation, 2.5 of them have triple coincident data. So it looks like the picture is not nearly as optimistic, but after about 5 years of taking data, one could hope to have something like a 3 sigma significant detection for memory. So it looks less promising than the study of Lasky et al., but I think it's still possible that within this decade, there will be statistical evidence for the gravitational wave memory effect. Okay, so what I've shown, I think, is that it's challenging to detect the memory effect, so why would we want to do this? And this, I think, will address Avi's question from earlier. And to do this, I'll remind you about Noether's theorem, which basically says that for every continuous symmetry of a system, there's a corresponding conserved quantity. And some of these are familiar, probably like time and space translations, which have corresponding conserved quantity as energy and linear momentum. Rotations have a corresponding conserved angular momentum. There's a slightly less familiar one, which is Lorentz boosts, which would be the final symmetry of flat space-time forming the Poincare group. This has as its conserved quantity what people sometimes call, excuse me, center of mass angular momentum, which is mass times center of mass position in the rest frame of the system. Sorry. So one can ask the question, these are the symmetries of flat space-time. Are they also the symmetries of space-time that become approximately flat, far from an isolated system like a black hole? And that turns out to be not the case. There's a larger group called the Bondi-Metzner-Sachs group after its discoverers. And you can ask, well, what's the difference? Well, there still are rotations in Lorentz boosts, but the translation part of the group differs. And instead of being just these 4 degrees of freedom, it turns out to be infinite dimensional. So I won't define this precisely, but I'll give you an intuitive picture for what these additional transformations are. So one can imagine a translation in the following way. Suppose you have a bunch of observers shown with dots here who are at some large distance from a source. And suppose they all translate by the same amount delta x. Of course, this would be equivalent to just translating the central black hole by some small amount delta x. And this would obviously change some property of the space-time, but doesn't change the leading properties as you go to very large distances, basically infinitely far away. But what Bondi, Metzner, and Sachs showed is actually there's no reason to have all your observers translate by the same amount. They should be able to translate by a bunch of different arbitrary amounts, delta x1, 2, etc. And the asymptotic properties of the space-time will still remain the same under this kind of transformation. Of course, they'll no longer agree on how much the black hole shifted, but it turns out there's not a coordinate invariant way of describing that anyway, so that shouldn't be too relevant. But where this ties into Noether's theorem is that if there's now an infinite number of symmetries, there's an infinite number of corresponding conserved quantities, which get called supermomenta. Now there's one additional complication which I didn't mention, which is that I'm talking about systems where you can actually radiate some energy. So there's not a true time translation symmetry, it's just an asymptotic one. And it turns out that instead of these quantities being exactly conserved, they satisfy a balance law, so that the change in energy is just equal to a flux of energy carried off by gravitational waves. So this schematic formula that I showed several slides ago, where I had changes in conserved quantities and a flux, this is actually the expression that you can compute, the conserved quantity associated with supermomentum. So these changes in conserved quantities are the supermomentum. And what it says is that you need gravitational wave memory to have this supermomentum balance law hold. So this is the interesting part of the asymptotic structure that you learn from studying the gravitational wave memory. So namely, what I think of as sort of the three most interesting points that you learn from measuring the memory is first, that the energy in gravitational waves radiates like any other quadrupolar source. Second, that this supermomentum conservation applies to real binary black hole mergers. There is this true BMS symmetry in nature. And finally, in this calculation, I've always assumed that the final state is just an isolated curved black hole, perhaps boosted. So basically what you'd be showing also is that if you measure the memory as expected, then the final state is some curved black hole without, say, any weird additional super translation error or something. So there's a number of interesting theoretical results that one would learn from detecting the gravitational wave memory. All right, so this perspective on memory and symmetries also led to the discovery of some new memory effects. So about 10 years ago, the symmetries of asymptotically flat spacetimes were revisited, and it was realized that there are new kinds of symmetries, which Barnich and Trosser called superrotations, which one can think of roughly as something like an angle-dependent boost and rotation. And there are corresponding conserved quantities, which are sort of the generalization of the standard angular momentum and the center of mass angular momentum, which are called superspin and supercenter of mass. So one might ask, does this relationship between symmetries, conserved quantities, and memories still hold up? And the answer is yes. There actually are two kinds of new memory effects, which were called spin and center of mass memory. So this spin memory effect, it's an interesting effect. It was found not to be a change in the gravitational wave strain itself, but in its time integral. But otherwise, it has a very similar form. There's three sorts of terms that produce it. The one in which it was discovered was in terms of changes of these superspin charges, which would occur, for example, if you had some unbound spinning objects scattering, they would produce such a change, and this was the first context in which it was discovered. In principle, if you have something like a core collapse supernova, where the neutrinos actually carry off some angular momentum, then you could, in principle, produce such a spin memory from this source, but I haven't seen any calculation of this done. But what I did compute is that the spin memory produced by the flux in angular momentum for solid angle in gravitational waves. So it turns out there's a relatively simple sort of Newtonian expectation for what this effect is, that if you look at this change in the time integral of the gravitational wave strain, it turns out to appear in the cross mode, and it's proportional just to the change in the reduced mass times GMA. So namely, it's the total angular momentum radiated by the binary as it shrinks from large radii to smaller radii. And it turns out, in fact, that this term had been found in a high order calculation in V over C squared, so at V over C to the fifth, or 2.5 post-Newtonian order. But it wasn't really interpreted as being related to this spin memory effect. However, in terms of observing this effect, LIGO doesn't really have any way to directly measure the time integral of the strain. But if you do have some offset in the time integral of the strain, then it's obviously produced by some sort of pulse. And what this pulse looks like is shown here. I computed it in an approximate way from this formula I showed on the previous slide. And then I compared with fully numerical simulations. And as you can see, they qualitatively but don't quantitatively agree. And essentially what one would then try to measure is at early times, their LIGO detector, you wouldn't have any, say, additional strain of the detector, but during this pulse at point 2, it would be distorted, and then at late times it would just return to its original configuration. So there's some very small effect that one would, in principle, be able to measure from associated with this spin memory effect. So again, this is just some sort of signal, and one can estimate how prominent it would be in different gravitational wave detectors, namely what's the signal to noise. It turns out for the LIGO detectors, it's extremely small. And even for the 3rd generation detectors, again, these are shown sort of average angle average values, so not the ideal case. You can see they cluster somewhere around 0.1 or slightly less. So it's unlikely that you would be able to measure this spin memory effect from an individual binary black hole. But the question of whether you can do some statistical measurement hasn't been addressed yet, as far as I'm aware. All right, and then it turns out there's one more additional memory effect, which I'm calling the so-called center of mass memory. So this is related to changes in these super center of mass charges and the corresponding flux of this center of mass type of angular momentum. And again, it results in a quantity that's a change in the time integral of the gravitational wave strain. And it turns out for this quantity, actually any source of gravitational wave memory can produce this effect. Again, there's the usual question mark of whether something like supernova neutrinos could produce it. I'm not sure about this yet. But binary black holes can also produce this effect. So I repeated a similar sort of calculation and computed what is the amplitude of this effect for these 2 parts from binary black holes. One due to changes in these supercenter of mass charges. And again, there's sort of an interesting Newtonian formula that you can compute. They turn out to be proportional just to the total mass of the system times sort of how much the memory has accumulated. That's what this expression is right here. So it's easy to understand this part. The flux part is a little more complicated, but it only appears when you have, say, non-equal masses for non-spinning systems, and it vanishes for equal masses. Again, there's the same caveat that this time integral of the strain is not something that you can measure, but there is some strain associated with this that you could in principle measure. And it would again be something that just produces, say, a half cycle of gravitational waves. But based on some preliminary calculations, these are very high order in terms of V over C and seem not so promising in terms of their detection prospects. They turn out to be both weaker. Both of these effects turn out to be weaker than the corresponding effects for the spin memory. So this may have to wait until some futuristic 4th generation of gravitational wave detectors. Okay, I think I'm running a bit short on time, so I was going to say a few words just about future directions, things that I'm working on. So one was about these things called persistent observables, where it turns out there is a number of different types of memory effects, this sort of standard memory, spin memory, and center of mass. And then there's also a number of memory-like effects related to the changes in the velocities as opposed to separations of observers, changes in proper time, and relative rotations of inertial gyroscopes. So we were interested in asking the question, are there some kinds of experiments, or at least Gedanken experiments, that one could do to actually measure all the memory effects in one covariant procedure. And it turns out that there are such procedures. It's just that they're not unique. There's many ways that one can do this. So we've understood these in sort of simple contexts, but now we're working to understand if there's a sort of more unified picture of how one might actually measure memory effects in terms of these other observables. A second point, which I, excuse me, wanted to mention, because it was to some extent actually asked, was if you have some modified theory of general relativity. So we considered a specific theory, and by we, I mostly mean a good grad student at the University of Virginia, Shami Tahura, who's finishing up her PhD. In these modified theories, you can have things like additional polarizations of gravitational waves, and associated with these additional polarizations, you can have new memory effects. So this would be these, in Braun-Sticky theory specifically, these memory effects are related to scalar polarizations. So they're a kind of breathing mode of the gravitational waves. And it turns out that these scalar type memory effects are not constrained by symmetries and conserved quantities, as I've shown, at least in Braun-Sticky theory, but they do come into the computation of memory effects. I don't think it's specifically the case that they would only appear in the memory effects. They would also appear in, say, the oscillatory part of the waveforms. So you would also find their presence there, but it is interesting that you need to know these memory effects to compute all the standard spin and center of mass memories that I described before. All right, so at this point, I'd just like to summarize some of the main points that I made throughout this talk. So what I hope to have illustrated through this talk is that the gravitational wave memory effect is this interesting nonlinear dynamical space-time effect, which LIGO and Virgo can discover, although only statistically. It's interesting to measure in particular because it is this observational consequence of von Metzner-Sachs symmetry, that to have von Metzner-Sachs symmetry and to have the gravitational wave memory, he constructed explicitly from supermomentum balance. So it's really, if you want to show the existence of this BMS symmetry, it's the most natural observational way to study it. And then there's the hope that future detectors like Cosmic Explorer and Einstein Telescope, when they're built, will be able to study it more precisely. In terms of these other memory effects, there are two new kinds of memory effects, the spin and center of mass memory. And I'd say the spin memory is possibly measurable by Einstein Telescope with stacking, although more work is needed to show this more definitively. But the second memory effect, I think we'll have to wait for even more futuristic detectors. So that's all I have prepared for today. So I will be happy to take any questions or have further discussion at this point. Yeah, thank you.
Yeah, thank you. Thanks, David. Now we can have some questions. Avi, you're first.
So you mentioned the mass, of course, in the energy radiated is causing this memory effect, and also the spin.
Mm-hmm.
Obviously, so black holes have three classical properties: mass, spin, and charge. And so I was wondering, I mean, obviously astrophysical black holes do not have a charge, but potentially you could imagine having a memory effect associated with electric charge. And did anyone calculate that? And for astrophysical black holes, I guess it's completely negligible, right?
Yeah, so for astrophysical black holes, I don't believe anyone's computed it. There is an electromagnetic analog of the memory effect. And essentially what it does is it, instead of leading to this relative displacement of nearby observers, it leads to a relative kick of test charges. So there is, in principle, another effect that you can measure. So
did anyone calculate it?
I don't know specifically in the astrophysical context.
No, just in principle, taking a Reisner-Nordstrom black hole, a charged black hole, and calculating the memory effect.
I'm not aware of anyone who's specifically done this calculation, although I wouldn't, I wouldn't vouch that it hasn't been done either.
Okay.
I've been involved with a number of conversations with experimentalists about measuring the electromagnetic memory effect, and like the gravitational memory effect, there's several forms, but you wouldn't try to measure it with, it doesn't need gravity. So much more promising, it's so much more promising things with much bigger electric fields are like, for example, at colliders. At LHC, you might try to measure it. You might try to measure it at the beam dump. You might try to measure it with neutron interferometry.
But what is the effect, Andy? Can you explain? So you have two charges colliding, and then what?
Well, there are different ways of saying it. You could say the way David said, that you have a velocity kick, but you can also think of it as a relative phase. It's actually a lot like an electric. There's the magnetic and the electric Aharonov-Bohm effect, and the electric Aharonov-Bohm effect can be thought of as a special case of electromagnetic memory.
Oh, really?
And interestingly, the magnetic Aharonov-Bohm effect has been measured, but the electric one, there's several dozen papers, attempts, people have made it. I don't know why it's so hard. Maybe these people they're not just that motivated, but it just hasn't become a central thing. But I mean, there is, in fact, I was just giving a talk last week at a CERN, Alice. They're interested in measuring this, and they asked me to give a talk there, and I had a discussion with them about various ways that you might measure the electromagnetic. They think of it in terms of measuring soft photons, but it's the same thing, right? Because
it's the same BMS. I mean, you learn the same thing, or you learn something.
Well, interestingly, so the BMS symmetry, we discovered is the same thing as the soft theorem, but the soft theorems were first discovered in electromagnetism. So it's a weird effect that was understood in gravity before it was understood in gauge theory. And there's also a symmetry. There's an analog of BMS symmetry in electromagnetism. The BMS symmetry are large, as he explained. They're related to diffeomorphisms that don't fall off at infinity, and in electromagnetism, they're gauge transformations. And there's also a color memory effect, which they're also hoping to measure at this newly funded, possibly at Alice at CERN, or at this electron-ion collider that's going to be at Brookhaven. Quarks undergo a color rotation. So there's a very rich, set of ideas things that have only been understood in the last decade or so that should lead to new experimental signals. And it's pretty bizarre that gravity is at the vanguard of this. And there are funny reasons that it's hard to measure in electromagnetism, and because of confinement, at LIGO, you have to measure the memory effect before the pendulum swings back. At the electron-ion collider, if you want to measure it, the memory effect in the quark-gluon plasma, you have to measure it before confinement kills you. So you've got even less time. So weirdly, gravity. These are subtle infrared effects, and weirdly, gravity is the easiest place to measure. But I think that they're all gonna be measurable, and they're all interesting in different ways and related to basic symmetries of nature.
This is fascinating. Andy, you should write a review paper linking all these different symmetries.
Well, I actually did write a book on it.
Oh, really? What is the name of the book?
It's called, I mean, the book came out in 2018. It's called Lectures on the Infrared Structure of Gravity and Gauge Theory. But the you know, the experimental exploration of this is, you know, ramped up more in the last couple of years, though it's far from, I mean, I think David is still a voice of the wilderness talking about measuring gravitational. I mean, well, I know Ray Weiss is very excited about, and in fact, Ray Weiss is very excited about gravity. In fact, he came to me with a proposal using neutron interferometry for measuring electromagnetic memory. We looked at it. It could work. I don't know, but you know, we didn't run it down all the way to the end. But yeah, I think it's there's a lot of interesting physical phenomena that are connected with symmetries that we don't. That's what makes what David's talking about so interesting to me, because there are a lot of things that you could measure. You could measure PPN parameters and so on and so forth, but this is in a different class. You know, it's measuring some very basic fundamental aspect of general of general relativity that, you know, really, I mean, Bondi, Metzner, and Sachs set out to show that at long distances, general relativity reduces to special relativity. That's what they, and it doesn't, because of the memory effect. They wanted the symmetry group to be the Poincare group, and it isn't. And this was, I think that people tried to kill it for years, and then eventually it was understood not only that it was real, but that it had observational signals, which were on the cusp of measuring. So I think it's very exciting. You know, new symmetries of nature are very exciting.
Yeah.
But let me ask him, what about LISA? Isn't that like a really nice place to hope to measure memory effects, or what you didn't?
Yeah, that's right. I didn't measure LISA, but let me actually have the results. I just didn't make the cut. Oh, sorry, was someone else talking?
Yeah, I was just saying that for supermassive black holes, or supermassive black holes coupled with small things, the CM symmetry should be bigger, right? The M1 minus M2.
Oh, for
spin memory.
Yeah.
Oh yes, for the center of mass memory. Yes, yeah. So basically, what goes on in the center of mass memory is you need a kick. So you need to have some gravitational recoil. So you need to radiate gravitational waves asymmetrically. And if the mass ratio is too extreme, then right, you can't really get much of a recoil. If you have a small black hole plunging into a much larger black hole, you don't get much recoil. So there's actually sort of a sweet spot for the center of mass memory. I was going to mention LISA, but I was running short on time, so this didn't make the cut. But for those who aren't aware, LISA is a planned mission led by ESA with a substantial NASA contribution. I'm actually a part of the LISA consortium. And it's much larger, so it's 3 satellites, which will be launched into an Earth-trailing orbit. The separation between these satellites is 1 million kilometers. And because of the larger distance and the different interferometry techniques used, its peak sensitivity is in the millihertz range. So that means you're sensitive to much larger black hole masses. So the supermassive black hole binaries between 10 to the 5 and 10 to the 6, 10 to the 7 is where it's most sensitive. Oh, I'm showing the spin memory, I think. No, this is the right one, sorry. So basically if you have a supermassive binary within about 10 gigaparsecs, so a redshift of, I don't know, whatever it is, somewhere between 1 and 2, then there is a good chance you'll measure the memory effect with LISA. So I would say it's a competitor for the third generation detectors. But the main uncertainty with LISA is just whether you will have this supermassive binary black hole merger at this redshift during the whatever 4 to 10 year operation period of LISA. And there have been some studies based on population synthesis models of supermassive black hole mergers throughout the history of the universe, and they have optimistic and pessimistic models, and the more optimistic models suggest sort of order 1, but some very pessimistic models suggest it will be 0. So LISA as an experiment is very promising for measuring the gravitational wave memory, but it's just that we don't really know whether the sources will exist at this point. So if LISA finds a supermassive binary within redshift of 2, you should measure memory, but LISA's not guaranteed to find such a source.
Let's see. I have a question about that. So LISA's much bigger.
Mm-hmm.
So it measures things at longer wavelengths.
Mm-hmm.
And I understand that the sort of the orbit times of supermassive black holes or around supermassive black holes and inspirals and so on, that those are going to be the right frequencies for LISA to measure. But what about, could you imagine that you would have some small merger and you only, because the memory is the long wavelength part of it.
Mm-hmm.
So why couldn't you have a small, is the signal just the amplitude too small? What if you have a small merger?
The amplitude is too small, Andy, because remember, LIGO's amplitudes are 10 to the minus 20 something, 21 to 24, depending on distance, whereas LISA has amplitudes of 10 minus 15 sensitivity, kind of. So
is that what it is? So
mm-hmm.
I guess there's a trade-off there. It might be that you can't see the waves, but you can see the kink. Wouldn't there be sources where you can't see the fine structure, but you can see the long wavelengths? But these are inertial detectors, right? So they don't swing back like the mirrors on LIGO.
Yeah, but the sensitivity is not as good. That's the problem.
Yeah, I don't think I actually have a plot of the sensitivity curve, but if you plot strain per root hertz or something, or the absolute strain, LISA is just much higher. It's more on the order of, I think Avi said 10 to 15. I believe that's correct.
Yeah.
So.
You basically take the Schwarzschild radius and divide by the characteristic distance. You will see that the strain is far greater than that of a 10 solar mass black hole at the cosmological distance. And so, when it's a factor of 10 to the 5 to 10 to the 8 more signal, because the black holes are bigger. So that's what LISA is.
But there's also a cumulative effect, right? So the gravity waves the oscillations don't have a cumulative effect, but if you have a long orbiting period, the memory adds up. So if you have many, that's another way of saying.
So what you're asking is, what's the sensitivity of LISA to a stellar mass black hole merger very long after the merger? Yeah. That's interesting. I don't know if anyone checked that.
Yeah.
To first approximation, the memory is it measures, it's the change in the first, well, the exact formula, actually, it's the change in the first derivative, the third derivative of the quadrupole moment.
Mm. I understand the argument that you're making, that basically it'll look like a step function, and then the Fourier transform of a step function is 1 over f. So as you go to lower frequencies, in principle, there should be some very low frequency signal.
A pole, yeah.
Yeah, but the amplitude would be the amplitude would be smaller than 10 minus 21. That's the problem, that LISA is not sensitive to such amplitudes.
Yeah. I mean, so even if you go into the millihertz range, you know, even if it's truly 1 over f, your drop, you may be increased by a factor of 10 to the 4, but LISA's sensitivity is about 10 to the 6 larger. So I think it's just very hard. You know, LISA doesn't really have the requisite sensitivity to actually see it from stellar mass black holes. I mean, if you have something like 10 to the 3 solar mass black hole, then I think it starts becoming interesting.
It's a good question. Someone should check which black hole masses might be optimal for Andy's question. Yeah.
And also, if you have 20 events, they could add up. 20 mergers could, or if it's a very different, yeah. I wouldn't have thought that looking for mergers of supermassive black holes would be the most likely way to see a signal at LISA, but I don't know. I don't have a very good feel for these things.
Yeah, I mean, the supermassive black holes are, I mean, if one merges, then you have a good chance of measuring it. The other LISA sources are things like galactic white dwarf binaries, or these extreme mass ratio inspirals where you have, you know, a neutron star or 10 solar mass black hole falling into a supermassive black hole.
But keep in mind, David, this is what people are expecting. So many times in astronomy, you know, like I can tell you that before the first X-ray telescope was launched, people expected just X-rays coming from stars. And they said, there is no point in launching a telescope because we already see the X-rays from the sun, so we will see X-rays from other stars. Then it turned out there are many other sources we haven't imagined. So you could have intermediate mass black hole, you know, you might be surprised. So, yeah.
I'm a proponent of intermediate mass black holes.
It's maybe getting a little weird, but what about like primordial gravitational waves that carry a lot of energy and oscillate many, many times, and they're just sitting there going through that triangle? Could that?
So these would be very low frequency, though.
Well,
but not low frequency compared to. Is it low frequency compared to the time at which over which you watch it? I don't think it's. You could look at it. I mean, people have talked about measuring gravitational memory by pulsar, looking at pulsar timing, where you look at it, and then you look at it again a month later, and you see the signal is shifted.
By the way, Andy, now we cannot do that because Arecibo collapsed a few hours ago.
Oh, it collapsed?
Collapsed. The structure collapsed today.
I didn't hear that.
It was a very important element of the pulsar timing arrays. You're right that in principle, people could do that if we had another Arecibo, yes.
Yeah, I actually do have a slide on this. This is another thing that didn't make the cut, but
yeah.
But yeah, I mean, essentially, so this is a bit out of date. This is from 2015, but you know, what they've shown is sort of what's the data span you need, and then what is the expected number of events. And yeah, sort of the nanograv level, at least as of several years ago, was kind of this flat curve where you have 20 pulsars with kind of microsecond RMS timing residuals. And then some more futuristic scenarios, like if you bring this down to, I guess, hundreds of nanoseconds, then you obviously get an improvement. And then if you have some scenario, like if you have the square kilometer array and you have 50 such pulsars and they're 50 nanosecond timing residuals, then after maybe 20 years or so, you start getting into the regime where you hope to, you have a decent chance of detecting the memory effect from pulsar timing. But these would be from the most, supermassive mergers, like 10 to the 10 solar mass black holes or so. So it is definitely possible in principle, but from the current data that we have, it looks somewhat pessimistic.
Okay. Are there any more questions? Yes, we had a very nice discussion. If we don't have any more questions, let's thank David again for a very nice talk and a stimulating discussion. Join me in thanking him. We'll see you next week for our last colloquium talk.
Yeah, thank you.
Thank you, David.
Thank you.
Bye.